Alright, so hi guys, how you guys doing today? Good. You guys ready for the 4-day weekend? Yeah, okay, perfect. Alright, so let's finish up. Yeah, we have the holiday this coming Monday, right? Yeah. So anyway, let's start. We're gonna finish up the some sort of like a review on Jenkins 1 and 2, so you can hit this real organic chemistry sometime soon next week. Okay. So last time we talked about the organic compound structure. Okay, we tried to make the carbon and carbon, hydrogen. So we tried to make certain type of structure of the organic compounds in also skeleton form too. But only thing you really have to know is, once again, the carbon should have about 4 bonding unless there's a double or triple bond, and also the hydrogens are implied there. You don't see that there, but you can always assume there's a carbon and hydrogen. Okay. So if you were quite okay with this one, we're gonna move on to the certain kind of special form of the organic compound we call the resonance structure. Resonance structure is just kind of a uniform. So each each individual resonance form actually does not exist in reality. Only the resonance hybrid form is the one that you're actually going to find in the reality. But we just learned about this one is actually an important part of understanding how does organic chemical reaction will work in certain type of reactions. Okay. So anyway, so resonance form is even though the same compound, they can show you the different arrangement of a pair of electrons. So they're always going to show the change of the location of the electrons. I said the pair, but it's kind of for the most of the time. What you're normally going to see is the change of the location of the lone pair. Okay, and the pair of electrons in double bond. This is about what can I say? This is about like a 90% chance that if you see some resonance structure, it's because of there's a change of the location of the lone pair and also the pair of electron in the double bonds. Okay, so meaning the electrons in the pi bonds. Okay, you guys remember that, right? In the first week, we learned about the sp3, sp2. So the ones in the the p orbital can be, relatively speaking, can be more easily used to change the location of this pair of electrons. Okay, so let's have some example over here. So for example, if you have this type of compounds over here. Okay, let's say you have lose this one over here, but you have one lone pair here, and one lone pair here. So if you try to think about the formal charge, which is what we did the last time, what you can do is try to circle the carbon over here. Okay, and then you have a 1, 2, 3, and lone pair, there are always pair of electrons 1, 2. So it'll be 1, 2, 3, 4, 5. Okay, but the carbon is what? Group 4 element, right? But the carbon now has 5. So carbon at this moment, carbon has 1 more electrons on it. So electron is negatively charged. Okay, so this is why this carbon particularly negatively charged because of the 1 more electron on this carbon. Makes sense, right? This is the formal charge. So if that is the case, Later, about 2 months later, we're gonna learn about this one is what we call carbanion, meaning it's just a carbon with a negative charge. So carbon, anion, carbon. Anyway, I will get there soon sometime this semester. Anyway, so this is when it's negatively charged. This is where you can find the lone pair. This is to find also what? The pair of electrons in the double bond. So what they can do, those two can go move up to here. Okay? So on the here, then that pushes this one to go up here. Okay? Okay, so think about it. So this lone pair goes on here. Okay? So that makes double. Okay? And that will push one pair of electron here on the top of the oxygen. So they become single bond, they get an extra lone pair. Okay? So think about it. This one, to have this oxygen neutral in here, you already have a 2 lone pair, you just don't see it because it's implied there as well. So you already have a 2 lone pair on here. Okay? So if you try to circle this one over here, it'll be 1, 2, 3, 4, 5, 6, which is good because the oxygen is group 6. So now it has formal charge, which is 0 neutral, because good neutral means they're stable. Okay, so if they push, they're gonna have an extra lone pair that makes in total 1, 2, 3, 4, 5, 6, 7. So this is group 6, but now it has 7. So now negative charge were on the carbon, now it's on oxygen. Because now when it do, look at this one again. 1, 2, 3, 4. Now it's good. So you see the change of the location of the either lone pair and a double bond. These are 2 possible structure you can have for the same compounds, but you can put it in each individual resonance structure, so they can go maybe here and here back and forth. This is some example of resonance structure. So you can rearrange the location of the lone pair or the pair and the double bond, so you can have a very good possible structure of the same compound. Kind of makes sense. So the formal charge of the total compound has not been changed. Only thing that changed was the location of the lone pair and the double bond. I mean the pair, the electron were initially in double bond. Now it's in here and it's in over here.
So if carbon is single bonded to oxygen, do we assume that the oxygen has an extra electron?
Here, yes.
Okay, just
Extra electron, yes, perfect. Makes sense, right? Okay. I know I'll give you a little more. Okay? So what you can also do, okay? Maybe we can try to do some polyatomic anion ones. It's a pretty good one. So the good thing about this one is I don't know if you guys remember this. If you look at the chemical formula, always the first element you see on the formula is a center atom, except the hydrogen. So you sometimes see this one, but hydrogen is exception. You cannot put the hydrogen at the center because it's too small. So except the hydrogen, if you look at the formula, always going to be the first element is at the center, and the next one is the neighboring atoms. So if you look at this polyatomic anion here, carbonate here, is the carbon will be the center, and those 3 oxygen will be surrounding the central carbon over here. Looks like this. And here's one tip I can give you. If you look at the periodic table, the carbon is there, oxygen is there. Can you guys guess which one will be more electronegative? Perfect, oxygen, right? Because it's more on the right side And also if it's the more upper side, but they're on the same period anyway. But the oxygen is more electronegatively is more on the right side of the periodic table and also very top. So between carbon and oxygen, if you have two negative, like a formal charge, you know what the electronegativity means, right? Electronegative means that is the certain ability to pull the electron toward themselves. Okay? So meaning it is natural for this compound that assign the electrons, extra electron on oxygen than carbon. So whenever you assign the oxygen here, that's totally good way to start. And then here's the one tip I can give you. Whenever you have oxygen making on a single bond, that is the one that's going to have a negative charge. Because of the one with only single bond, meaning they have a 3 lone pair. Okay. The one with the double bond that has only 2 lone pair. Okay. So meaning if you try to count the electrons around this oxygen here, will be 6. 1, 2, 3, 4, 5, 6. So it's formal charge will be 0. But this one there'll be 3 lone pairs there too. So it'll be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So it has 7 and 7 instead of 6. So that means they do indeed carry the 1 extra electron. This negative charge. So if there is 1 and 2 in total, the negative 2 formal charge on the whole compound over here. Make sense, right? So what you see over here is also what? You have a lot of the pair of electrons in the lone pair, and also you have a double one right there. So what they can do is they can move this one around here to move electron to here. Like think about it. If you have this one goes in, this one goes at the top. So this one is negative. This will be neutral. And now they can move it to the here. This is negative. Now it's move it to here, and the lone pair goes to here. So maybe this one and this will be neutral. And either way you can do it. You can do it over there too. So eventually, what it really happened to this one is they just tried to reassign the negative charge over 3 different oxygen neighboring atoms. So what they actually going to do by changing the location of the lone pair and the pair of electron and the double bond is either they're going to assign the electron on these 2, or these 2, or these 2 by just switching it in. Makes sense, right? I mean, you eventually going to see that, double bond now is gone to the here in the chart, so it will be double bond. Well, you can have a double one here, or double one, meaning if you have a double bond here, you're going to have a negative charge on these 2. If you have a double bond over here, you have a negative charge on these 2. If you have a double bond over here, you have a negative charge over here. Okay? So eventually, what you're going to see is 3 possible scenarios. Either you have this one, okay? So once again, the one with the single bond is negative charge, double bond is just neutral. So you can have these 3 possible structure for the same compound, and those are resonance structures. Make sense, right? Yeah. So there's one more thing I want you to know is this is once again not a real structure, but it is important that they might do this in the transition form or in the certain specific time period when they move on to the certain specific organic chemical reactions. That's what we're doing this, but in the reality, what we're actually going to see is this one. Okay. This is what we call the resonance hybrid, meaning you just combine everything over here. So the logic is very simple here. So you never change the formal charge of the carbon or anything, so you can just leave it here. But the problem is you change the location of the lone pair on the oxygen or the double bonds and so on. So the basic thing is that you have a 2 extra electron to assign on 3 different oxygen. So it could be these two, or these two. So mathematically speaking, each oxygen will have a 2/3 chance to get a 1 electron, right? So if you don't want to do this, you can also do this in a one structure, which is easier and also more realistic model you can have. So I'll later tell you why this is so important. But only thing you really have to know is why the resonance structure is there and what really happened to those. Simply just moving those pair of electron from lone pair to the double bond to the lone pair. We can have a different type of structure, but we can also do the hybrid form, which is this one, and you have like a here and here also as well. It's somewhere between single and double bond too, and also you have a fractional number for the negative charge, which might be kind of hard to explain if you think once again if you see the electron as matter. When we try to develop or to build up the bigger and bigger compounds by assembling with the small elements and atoms, we actually use the theory of the orbitals. But the orbital actually we do use only by chance to find the electron. So it's simply meaning the chance to find the electron on each. So this is also kind of important here that whenever you have a resonance structure, you're going to have a delocalized electron. Meaning, whenever you get to the resonance structure, you really don't know where the electron really is, but by just chance. So especially on the resonance hybrid form, we normally say the electrons are delocalized, meaning you just can't locate it anymore. Because now you just sum everything just using numbers of chance. Makes sense, right? Okay. Perfect. Let's move on. All right. Can you guys maybe try this one? I'll give you about maybe 2 minutes. So once again, the first thing you see on the formula is the central atom. The one after is the surrounding. So you can put the sulfur at the center, and you can put the oxygen, 4 oxygen around the sulfur. Okay? And then you can assign the 2 negative charge. That means you have 2 additional electrons. So you just need to assign the 2 electrons among 4 different oxygen in your own way. Okay? That's pretty much it. Okay, just the first element you see on the formula is central atom. So put the sulfur at the center and put 4 oxygen around that sulfur. Okay, and try to assign, choose any 2 of oxygen and put extra electron 1 and 2, and leave the other 2 neutral. So the one that is neutral oxygen will make a double bond to central atom, which is sulfur. The one that has extra electron is negatively charged. It is going to make a single bond to central atom, which is sulfur. Okay, makes sense, right? It's just here. Just one example will be this one. Okay, makes sense, right? So you all got this one, right? Okay. Yeah. Oh, sorry. You all got this one, right? Okay. You good? Okay. So the thing is still, you have electrons on these two, but also these two, right? So if I draw, you can draw all the different possible structure by designing the electron on the electron oxygen. But once again, what I can do is hybrid. Okay. Okay, so you can do this too. So in total, negative 0.5 times 4 is negative 2. So
Is this like a real structure, or is this?
that is a more realistic model you may find in the experiment.
Okay, how does
Mhm.
sulfur have 4 bonds? I don't understand that.
Oh, it's possible because if you start from the here, how many electrons on the sulfur right now? 6, right? That's good. Yeah. So 4 bonds is different.
Okay.
That's a very good question. But I can say once again, this is more realistic. Actually, that was a good question. I want to add something more. Think of right. Yeah, I think they should be good anyway. So, any other questions? Are we good? You good? I can do one more if you want me to, but I mean, one more. Oh yeah, one more. Yeah, just one more. Okay. Try to do one more. Okay, can you guys try this one now? Phosphate. The phosphorus is group 5. And it now has 3 additional electrons on it. Obviously, it also goes to the oxygens out of 4 oxygens. Okay? Okay, so once again, the first thing you see is the central area except the hydrogen, and you just put the 4 oxygen around the phosphorus, and just try to put the 3 additional electron for each electron. The one that didn't get will be neutral with double. All right, so then, right? Okay, good. Because if you also look at the central atom, it also has 1, 2, 3, 4, 5. It's neutral, it's good. But 3. So eventually you're going to get and each one will have a 3/4. So in total, okay, it's good, right? So I think we're pretty good. I'll move on to the next topic, okay? And then, all right, so far so good. You guys are doing great so far. So next part is the how are you going to define the acid and base? So this is quite also big portion of organic chemistry, dealing with the different types of acid and the base and the certain chemical reactions. Okay, so there are a couple of things. I want to start with defining those terms, but the thing is we have 3 different ways to do it. So the first one is a Arrhenius definition. Okay. Second one is Bronsted-Lowry. The third one is a Lewis definition. I just want to tell you we are going to use these 2 often. Most of the time, we'll be happy with the Bronsted-Lowry, which is most frequently used for most of the chemists and scientists. But if we can't do it, if we can't use this one, we'll use the Lewis sometimes. Okay, just keep this in your mind. Arrhenius one is Not so much, because it actually limits a lot of sample that we also use in chemistry. So you don't have to worry about this one. So I'm not going to talk about it. But this one, I'll tell you. So Bronsted-Lowry, so in page number 2. So Bronsted-Lowry, in this term, the acid is the one that donates proton. Oh, sorry, protons. Okay? So if that compound donates the proton, we call that acid. Okay? In Bronsted-Lowry definition, the base is actually accept. So they're gonna steal the proton from somebody. Then, so they accept. Or you can say they steal the proton from somewhere. We call this base. Okay. The Lewis one is actually vice versa. So, you know, proton is positively charged, right? So the electron is but negatively charged. So in Lewis, what is that is the in Lewis acid will actually take the electron pair. That it will be almost the same job they're doing donating the protons. So if they accept the pair of electron in the chemical reactions, it will make Lewis acid because now they take negative charge, not donating. So it's same as donating the plus charge. Yeah, same here. So in a Lewis base, we're actually going to give a pair of electron to somebody else. So this is also same as they're accepting the positive charge, because they now talking of the opposite charge, but doing in counteractions. But we use the Bronsted-Lowry more often because it actually makes most of the chemical reaction we do in the lab. The Lewis is the one that when we get down to the very weak base, it's really hard to tell with the Bronsted-Lowry version that is obviously base or is obviously acid or something. That will have a more sensitive tool to define those in terms of acid or base. Okay, makes sense, right? Okay, perfect. Because in a chemical reaction, you're always going to see the motion of the electron, but proton-wise, you know, it's always work. But you may want to use Lewis sometimes because of that. Okay. All right. So why we care about those so much? What's the problem here? The problem is whenever you have a very strong like a acid, like a hydrochloric acid or other type of very strong binary acid. Okay. Meaning, you ever seen this one a lot of times in Jankin 1 and 2 will actually give you a lot of H+, which is hydrogen cation that is same as proton. Because the hydrogen is only made of what? One proton and one electron. But it becomes cation when it loses electron. So once it has one proton and one electron, but they lost electron, there's only one proton. So hydrogen cation is same as proton. Makes sense, right? And then it makes this is the one that takes the electron with. This is more electronegative. So this is why the hydrochloric acid is a very strong acid. They're going to give us lots of numbers of hydrogen cation, simply same as proton. So in Bronsted-Lowry definition, it is indeed acid here. So that is no problem. Okay, that is no problem. But the problem is, we call this one is so strong, almost 100% dissociation rate. So meaning, if you have a 1 mole of HCl, you can expect there will be almost 1 mole of protons as well. Okay, because it shows very strong acidity, meaning it will show you almost full dissociations between these two. So they can have lots of these two at the end. Okay, but whenever you have a weak acid, it means they're going to give you some protons, but not a lot. Maybe, so if there is a weak acid form like HA, they also give you H plus and A minus form, which is your base. Anyway. So if this is a weak acid, you're also going to see a lot of this, but there's still a lot of this one does not break up to give us the protons. This is what we mean by weak acid. So it does give us the proton, but not as much as the strong acid do. So in this case, we need to find out then how much proton this particular weak acid will give us. Like how much proton this weak acid will give us, right? That's the point, right? That is why we sometimes use
What
the
element is
constant,
A?
the Ka. You guys remember this? Kind of? Kind of, okay. So this is pretty much the same here. So this will tell you about what? You have how much of this one and this one will be there from the weak acid form. Okay? So this will tell you the acidity of your compounds. Okay? So this is what we call Ka. Okay? This is will give you some.
Dr. Cho, and the HA,
mhm.
what is A? You lost me there.
So A is anything that bound to the
Oh,
hydrogen.
okay.
So no, that's a good example. That's a very good question. So for example, do you guys like vinegar? You guys like the
Okay.
vinegar in your? I mean, it's a good, seasoning source. I know. So if you have this one, like acetic acid, diluted version of this one would be one type of vinegar. Anyway, this is also a good example of what? The weak acid. Because if it's a strong acid, you can't really eat vinegar, right? Anyway, so if that is the weak acid, this is your A, this is your H. So while we normally indicate the weak acid in form of HA, meaning the H is literally the H, anything except this H is A. So in this case,
So it's literally arbitrary.
it could be anything. Yes. Literally could be anything. So, yeah, sorry?
She said it's a variable.
I said it's just a variable.
Yeah, very, yes, perfect. Absolutely correct. So if that is the case, so if this is HA, H is just what? H plus, right? But the H, A minus will be just this one. Because now it lost over there. So this is one example I can give you. But literally, HA could be very, very different because of the A. Anything that A is this one. Yeah? Anyway, so it makes sense, right? Makes sense? Good, perfect. You guys are great so far. Okay. So if that is the case, I'm going to show you how you're going to use this Ka value. So obviously, if you have a higher number for Ka, meaning it will be stronger acid. Because if you look at this equation over here, if you have a higher number on Ka, meaning you have a higher number on numerator than denominator, right? Makes sense, right? Because whenever you have a higher number on the top, that makes your number bigger. So if you have a higher Ka, meaning you have a higher numbers of H plus and A minus. If you have a higher number of H plus, that makes this one more acidic. Because it means you have a more number of proton will be donated there. So a higher K means it's a stronger acid here. Stronger acid will show you high number for Ka. If it's lower, meaning it's weaker or weak acid, we can say. But the Ka, as you can see, it's a weak acid, so it's normally very small number, like 10 to time to negative fifth, negative 6. It's very small number because it's not so strong. You only give only very small numbers of protons. So instead of using Ka right away, we always do with the p-value. You remember pH, right? pH is what? Negative log of concentration of hydrogen cation. The pKa, we use the pK instead. It's literally negative log of your Ka. Okay? So here's the thing. This is a negative log, right? This is a negative log. So if you have a higher number in Ka, meaning you have a lower number in pKa. But it will give you much more nice integer numbers because it's in a log, right? But only thing you have to know is whenever you have a higher Ka, meaning stronger acid, that will show you lower pKa. But in a much better, nice form of the number. This is 1 or 2 figures of the integers. So this is something that I want you to remember over here. Okay, so one example I will give you is this one. Okay. I'll probably do this again. Don't worry about it. Okay. I'm gonna do this again. Don't worry about this one too much. I know we don't have much time left today. Okay, so we're gonna do the extra credit. So anyway, so this is acetylene. This is also kind of weak acid here, interacting with the base, which is OH minus, so they can make water and acetylene anion over here. And then when we try to decide, do you guys see this one here? This is kind of tricky one here. It actually show you the forward reactions, but also the reverse reaction. Okay, so meaning they can either go both way, because either one of the reaction of the reaction, yet they're dominant to each other. So they may have both like a forward and reverse reaction at the moments over here. But in this case, what we can normally use is the pKa value of this compound and say which one will be more dominant in which direction, relatively speaking. This is why whenever I give you a number for like a pKa, I probably give you a number for Ka sometimes, but either Ka or pKa, most of the time it will be pKa. The lower number you have that compound will actually show you more strong acidity over the reaction. So I'm gonna do this problem on Wednesday, not Monday, right? Okay, Wednesday. Okay, so I will stop here. Okay.